So what I want you to do is look for as many patterns as you can and see if you can find out what are the missing numbers in row 6, what are the missing numbers in row 7, and can you write down the entire row 8? And then once you think you've found the patterns, you're going to describe them to me. So 5 is going into this first box. Can someone tell me a pattern that they used to find that 5?
So for the third row, it's like 1 plus 2 equals like a 1 between that and the fourth row.
Okay.
So 1 plus 2 is 3, 1 plus 3 is 4, so 1 plus 4 is 5.
So you were using both of those to get the 5.
Yeah.
Okay. Another pattern. Someone see another pattern for how they came up with that? So you're looking at this one here. You went 1, 2, 3, 4, so it had to be 5. Okay. So there's 2 different patterns to see that same one. Anybody come up with another pattern? Okay, so there's a start. We've got 2 patterns for that one. Similarly, you got this one to be a 5 as well. And those same 2 patterns you could see there. All right. This one, 15. Can you tell me a pattern for coming up with 15? Again, this idea of taking these 2 arrows and adding the 2 above it works out again, yes. Anybody come up with another way to come up with 15?
So like you started in like row 4.
This one here?
Or, yeah, row 3.
This.
So like you add like plus 2 and then you add plus.
So plus 2, plus 3, plus 4, then this would be plus 5. Good. Anybody know what those numbers are called? They're a famous set of numbers. They're not the Fibonacci numbers. These are called the triangle numbers. The triangle numbers because if you make triangles, like that, this triangle has 1 dot, this is 3, then there's 6, then there's 10, the next one would have 15 dots. And the triangle numbers are also the sum of the first consecutive whole numbers. So this is 1, this is 1 plus 2, this is 1 plus 2 plus 3, this is 1 plus 2 plus 3 plus 4. The next one will be 1 plus 2 plus 3 plus 4 plus 5. And they show up in Pascal's triangle right there. Very fancy. So similarly, this one here is going to be 15 as well, because you have the triangle numbers coming in that diagonal as well. Did anyone come up with 15 in another way? Okay. So then, most likely you'll find that when finding the next item in Pascal's triangle, this technique works the best. Just adding the 2 above it to find what's next. That doesn't help us with our first number, but what do you think the first number is going to be? 1. So it'll be 1, then 7, then 21, then 35, then 35, then 21, then 7, then 1. And you have row 8. Yes?
If you think about it, there might be a 0 on the other side.
That's right.
of 1, so
There's nothing there, so if you add that nothing, you still get 1. And that's not a bad way to think of it.
found another way
You found another way to get a number. Good.
to 15.
Yep.
If you go from the 1 close to the 5, the 1 close to
This
5,
one?
That one, yeah. So 1 times 5 is 1 5, and then that's 3. No, go down to the next 15. That's 3 times. I don't know where I was going.
Okay. There are other ways. Sometimes I call this the hockey stick way. If you make a hockey stick by starting on any diagonal, the numbers in the shaft of the stick always add up to the number in the blade of the stick. So 10 plus 4 plus 1. That works for any length. So if I take this one away for now, and I do a longer stick here, 1 plus 3 plus 6 plus 10 plus 15 equals 35. Okay? So that's pretty cool. So there's a number of different ways of getting the numbers. Can you see that Pascal's triangle has symmetry? Okay? I mean, it's the same on one side as it is on another. Some other cool things about Pascal's triangle. We will find Fibonacci numbers in here eventually. That'll probably be the last cool thing that we find. Okay? But for right now, some other cool things that you find if you add up the numbers in the rows. The first one adds up to 1. The second one adds up to 2. The third one adds up to 4. Then 8. Then you add these numbers up and you get 16. What do you think the next one's going to add up to? 32. And what's special about these numbers? They're the powers of 2. So it's very cool that the second one adds up to 2 to the 1. The third one adds up to 2 squared. The fourth one adds up to 2 cubed, 2 to the 4, 2 to the 8, and so on and so on. Well, this triangle is just made by adding the 2 above it. And then once all the crazy patterns appeared in this triangle, then it became famous. Okay? And we haven't even touched upon why it's important for us yet. The other cool thing about this triangle is if you think of these not as numbers to add up, but actually digits, here we have 1. Whoa. The first one is 1, the second one is 11, the third one's 121, the fourth one is 1,331, the next one's 14,641. This one we'll talk about in a second, but when you look at those first 5, why are those important numbers? They're the powers of 11. This is 11 to the 1, this is 11 squared, this is 11 cubed, this is 11 to the power of 4. Now, 11 to the power of 5 is actually the following. 1, 5, 0, 1, 6, 1. What did I do? One, 5, 0, carry the 1 over, made this 11. Carry the 1 over, made this 6, 1. If you try 11 to the power of 5, sure enough, it's 161,051. 11 to the power of 7 is going to be 1, 6, 5. Carry the 1, 21. Carry the 2, 7. Carry the 1, 7, 1. And if you try 11 to the power of 6, sure enough, that's that. That's pretty crazy. So we have our powers of 11 built into here. Combinations are built into here. That's what we're going to find out on the next page, so I'll leave that for now. But the last thing I'm going to show you is Fibonacci numbers. Fibonacci numbers can be found in Pascal's triangle through the following magic line. Oh, magic. Okay? Now this is a magic line because if you trace this line down again until it hits another number, you hit 1 again. When you trace that magic line down again, this time you hit 2 numbers. If you add those numbers up, you get 2. If you trace it down again, the next time you hit numbers, you hit the 1 and the 2, which adds up to 3. Trace it down again, you hit the 1, the 3, and the 1, which adds up to 5. And every time you trace this number down again, you hit the next Fibonacci number. 1 plus 6 plus 5 plus 1 makes 13. And you get the Fibonacci numbers in Pascal's triangle. 1, 1, 2, 3, 5, 8, 13, and so on. But it has to be this exact magic line with that little bump at the end, otherwise it doesn't work. Yes, you can go to the washroom. So now we're going to look on the next page. Well, we could determine the next one. We could write down row number 9, but we could evaluate each of the following combinations, either by hand or with a calculator. I'm going to tell you that 4 choose 0 is 1, 4 choose 1 is 4, 4 choose 2 is 6, 4 choose 3 is 4, 4 choose 4 is 1. What do you notice? What does that match up with? Matches up with one of the rows of Pascal's triangle. If you chose any value between 2 and 7, say you chose 5, and you did 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5, that's it. What would you get? This is 1, this is 5, this is 10, this is 10, this is 5, this is 1. Does it match up with any of our triangles? What row is this in our triangles? The 6th row. So as far as filling out our chart goes, we start with row 1 being 0 choose 0. You have no things, you choose none of them. How many ways can you do that? One way. Just leave everything be. You have one thing, you don't choose it. You just leave it there. There's one way to do that. One way, choose 1, there's one way to do that. So fill in the rest of this with your combinations. And then once you've filled that in, take some time to think about this. What is the relationship between the row number and the value of n? What is the relationship between the rth number and the value of r? Use your results to describe the location of 11 choose 8 in Pascal's triangle. All right, the last interesting thing that can happen with Pascal's triangle. I've already shown you where the fancy Fibonacci numbers are. I will now show you where the fancy Sierpinski triangle is inside Pascal's triangle. Do you know Sierpinski's triangle? Sierpinski's triangle looks like this. Instead of drawing it for you, I will just show it to you. There it is. There's an image. There's Sierpinski's triangle. What's cool about Sierpinski's triangle is that if you zoom in on it, it repeats itself. So this triangle here is a repetition of this one. And if you zoom in more and more, it's just triangles within triangles within triangles, and there keeps having holes within it. And I just learned the other day that this is something that actually is between 1 and 2 dimensional. It's a weird thing that way. It's more than 1 dimensional, but it's not quite 2 dimensional. It is weird. So Yeah, I was learning about the study of non-whole dimensional objects that are in between. And actually, non-whole dimensional objects become important. This is something called a fractal. So as you zoom in on it over and over and over again, it repeats itself. And now they're finding out that fractals are very important for building like antennas in cell phones. So you can get the best cell service if they try to make the antenna as much like a fractal as possible. Okay, but this is Sierpinski's triangle. How do we see Sierpinski's triangle in between here? Well, you can find it by shading in all of the even numbers. If you want to be even fancier, you can shade them in with a triangle. And if you would keep going with this, it would create a bigger and bigger and bigger Sierpinski triangle. The next time you have even numbers, it will be a very large triangle right in there. And then there will be two smaller triangles off to the side, and so on and so forth. And the more you do and the more you shade in, you will get a bigger and bigger picture of Sierpinski's triangle. Okay, so that's the last cool thing as far as an application for Pascal's triangle that we're going to look at right now. And right now we can go to 8.4, no, 8.6. And start up with this warm-up. There's a line in Pascal's triangle. Tell me which row it's in. How do you know? Can you write this fifth term? 1, 2, 3, 4, 5, 330. In n choose r notation, that would be 330 equals what choose what? So think about Pascal's triangle. You need a number here, and we need a number there. And then once you have that, you can take out your calculator to check if you're right. Yes, 11 choose 4 works. Okay, we are going to skip over this and go to this on the next page and look at how we're going to use Pascal's triangle and combinations to connect to something called the binomial theorem. The binomial theorem is looking at what happens when you have a binomial and you put it to a power. Now you have done squareds quite a bit. You'd have to FOIL that out, x squared, x plus y times x plus y, and if you multiplied that out many times, you would get 1x squared plus 2xy plus 1y squared. If you decided to multiply that by x plus y again, by the way, anything to the power of 0 would be 1, right? And then again, a pattern starts to happen. If we look at the coefficients, they match up with Pascal's triangle. Now, part of what is happening here is if I multiply x plus y times x plus y times x plus y. Whoa. Let's try that again. to the power 4. That would look like that. Now, while you're multiplying all of this out, what is basically happening as far as combination goes, and we're going to look at this one, 4x cubed y. In order to get x cubed and a y, you're going to need to choose 3 of these x's and 1 of the y's when they get multiplied together. In fact, if you did an arrow thing of everything that could possibly happen when you're multiplying this out, and we usually don't go to arrow things past 2 because the arrows get too confusing, but one possibility is that this x gets multiplied by this x, by this x, by that y. And that would give me 1x cubed y. Can you see another way that I could get an x cubed y? I could get another x cubed y by choosing this x, this x, this x, and this y. That would give me another x cubed y. How many different ways could I get an x cubed y? 4 different ways. It, in fact, is the same way as deciding, well, in order to get an x cubed y, I have 4 y's, I need to choose one of them. And what's the coefficient here? 4, choose 1. How many y's are in this one? Well, it'll be the amount of ways of taking the 4 y's that are there and choosing 2 of them. So there'll be 6 ways that you can get an x squared, y squared. Does it make sense that there's only one way to get an x to the 4? Because you have to multiply all the first ones all the way through. And just like the y to the 4, the only way to get that is to multiply all the last ones. And so your combinations and your permutations show up in the binomial theorem. And what we're going to do is we're going to summarize this, and we're going to figure out how we can use this to figure out any term in any expansion quickly and easily and develop a formula from it. Okay? Something to notice as well. Some patterns to notice. And the way that I like to remember it is I like to remember it from x squared, because that's one you can easily multiply out in your head. One thing to notice is that if you have x plus y squared, there are 3 terms. There's always one more than whatever your exponent is. So if you had to expand x plus 7 to the 15, how many terms would there be? There would be 16 terms in the end. You would know the first one is going to be x to the 15. You would know that your last one is going to be 7 to the 15. Right? And notice when there was a 4 here, it goes 4 choose 0, 4 choose 1, 4 choose 2. So the next one would be 15 choose 1. Then you would have x to the 14 and 1 7. Later on, we'd have to simplify that by multiplying the 7 times the 15. The next term will be 15 choose 2, which is already a pretty big number, 105. 105, then there would be an x to the 13 and then a 7 squared. And so another pattern that you might have noticed is that you start with x to the 4, then x3, x2, x to the 1, then there's none of them. And the y's, whatever the last thing is, starts with none of them, then 1, then 2, then 3, then 4. In fact, because when I drew out all 4 of them, what's happening each time when you multiply these out is you're always choosing one term from each set of brackets. So your exponents in the middle always add up to 4. Because you could choose 1x and 3y's, which adds up to 4, or you could choose 2x's and 2y's, because you're always choosing one thing inside each bracket. So it's another pattern to notice that the exponents always add up to what you started with. Now we're going to be expanding some things with not just 1x and 1y. We'll be expanding whatever we want as the first term and whatever we want as the second term as we go through, as you'll see when we get to example 1 in the beginning of tomorrow's class. Right? You've got a 3b minus 1 to the power 4. Okay.